right. Everybody okay? And you'll get out of that, you'll get 3 eigenvalues. And when you do this, you'll solve the eigenvalues. What you get is you get lambda 1 equals v0 over 4. You get lambda 2 equals 1 plus kappa v0 over 4. And lambda 3, you end up with 1 minus kappa of v0 over 4. Okay. So this would be, okay, so what that means is the following. If I come over here, that means I'm going to come over here. This is v0 over 4. Then there's going to be an energy up here, which is going to be 1 plus kappa of v0 over 4. And then down here, there's going to be 1 minus kappa times v0 over 4. So what you find out is that when you do turn on this perturbation, this thing that was triply degenerate splits into 3 different energies.
That's figure 6.6, right?
Yeah, figure 6.6, yeah, as if it were being turned on. All right?
Give you the value of kappa.
Yeah, kappa is just a number. It's like 0.2, set 0.72. Okay, but last week we talked about diagonalization, all right? And this is an important idea. This is, what Dale mentioned is this is like diagonalization of a vector. Okay? And so here's what all of that means. Okay. When I have a vector like this, where the terms just go along the diagonals, that's a diagonal matrix. There are no off-diagonal, no off-diagonal terms. Okay? What that means is the terms along the diagonal are the eigenvalues. And what it means is the basis that you used here are the eigenbases. So when you have a diagonal matrix, this is a diagonal matrix. And what it means is the diagonal elements equal the eigenvalues. All right? And it means that psi A0, psi B0, and psi C0 are the eigenfunctions. Right? So when you have a diagonal matrix, it means that the basis set that you're using, psi A, psi B, and psi C, those are the eigenfunctions, and these are the eigenvalues. All right. We came over here, and we had the overlap matrix that is clearly not diagonal. Okay? You have these terms, which are the off-diagonal terms. So what does that mean? One, it tells me that I don't know what the eigenvalues are because it's not diagonal. And worse yet, because it's not diagonal, what can I tell you about my psi A, my psi B, and my psi C? They're not the eigenfunctions. All right? So I don't know what my eigenvalues are now, and I don't know what the eigenfunctions are. Okay, so the first step is to solve the secular equation. And when you solve the secular equation, what do you get?
What does it?
You get the eigenvalues. All right? So the next question is, well, geez, now I have the eigenvalues. Can I figure out what were my eigenfunctions? And the answer is yes, you can. What you do is you take the original, you take each eigenvalue, and when you take the eigenvalue, you plug it back in to the original equation. And when you plug it back in, you'll be able to find the 3 eigenfunctions. Right? It's a great exercise, and when Griffiths does it, he comes up, he doesn't tell you how to do it explicitly, he kind of gives you a hint. He gives you that, you know, that,
Is it because we did it in chapter 3?
yeah, we've done it before, yeah, we've done it before. What he gives you is that psi, I guess it's psi 1, okay. So, the question is should it be psi 1, 0, or should it be psi 1, 1? And here's the other big idea, that as soon as we do find what diagonalizes this for the energies, what does it tell us about these functions? That they were no longer our basis, right? So therefore, we need a new basis. So it would be psi 1, 0. It's all the way back here. So it's saying that, you know, psi A, psi B, and psi C, where it's a 1, 1, 2, and a 1, 2, 1, and a 2, 1, 1, that wasn't a good basis. Those weren't my good quantum basis. Those weren't my good quantum numbers to begin with. That what I really needed was something else, so that when I turned on the H prime, I got these. So what happens is, and now it's kind of trivial when you look at this. Look at our original matrix. Is any part of this diagonal? Kind of like this top one. It doesn't have anything else. It's not sharing anything. Not sharing anything there. Not sharing anything there. So maybe that's going to be one of the bases, right? So what basis would that be? That would be psi A. So one would be psi A. And then what is it saying about psi B and psi C? That they're no longer good as they are. There's some type of combinations of each other. All right? And right away, the combinations are 1 over radical 2, psi A 0, psi B 0 plus psi C 0, where I put the 1 over radical 2 to normalize it, and then 1 over radical 2, then psi B 0 minus psi C 0.
So you get those solutions after you go back and solve the original equation.
Right, you can get them by putting them right back into here. Okay?
Because there was zeros with the first one, we could just determine right away that it was just psi A.
That's right. You can see it by these. It's not mixed. So just now, a little bit of linear algebra, you can see that this unit vector is not mixed with anything else. So I know one of my basis vectors is going to be psi A, and then you can see the B and C, they mix with each other.
Which is plus or, usually it's plus or minus.
Yes. Okay, now, how about if I did this now? What if I called this psi A nu, called this psi B nu, and this psi C nu, and I use these three as my basis. So this is my new basis. And then I computed Wij matrix, but in the new basis. What do you think that would equal? What's that there? Okay. It would be a diagonal matrix. Like in this case, for the eigenvalues, it would be V0 over 4, and then 1 plus kappa V0 over 4, and then 1 minus kappa V0 over 4. And that would be 0, 0, 0, 0, 0, 0. And that's why it's called matrix diagonalization. That when you start with a matrix that isn't a good basis set, right? And then you find the eigenvalues and the eigenvectors, those eigenvectors are the good basis set.
Which lets you create the diagonal matrix that you want.
Right, so in other words, if you created this matrix right here, it would be diagonal. You'd say, and the conclusion is, these are my eigenvalues, and whatever basis I used
your functions.
what are the eigenfunctions about those eigenvalues. And that's called a matrix diagonalization. All right?
It reduces to the unperturbed case. If your kappas are 0, it's just the scalar potential matrix.
Okay. Okay.
Which is what you expect.
Yeah. All right, and so here's the scoop then, is that what you say over here is, are these the good eigenbasis then for the total Hamiltonian?
No.
So with the total Hamiltonian, the perturbed
Side
Hamiltonian,
A, yes, but the other two.
but for the excited states, they're no longer, so in other words,
Well,
Nx, Ny, and Z are not good quantum numbers. You've got to know two sets of them, right? You got to know Nx1, Na1, Nax1, Nay1.
well, for NA, it was the same before and after, because it was,
Right.
so that one was all right, it's just the other two were the degenerate states.
Exactly. Okay, so you got the idea of the matrix diagonalization, and then you get a feel when you see a matrix, what you can conclude from them. It's very important stuff to know. Okay, so now let
It's
me
not
show.
that one of them's going to be the energy from before the split, and the other two are going to be something different.
Yes, oh, by the way, so let me point out, this is what problem 6.6 was about, Alvin. You asked at the beginning of the class. This is what 6.6 is about. If you go to 6.6 now, on page 260, it is asking you those questions. You know, it's basically asking you, what are you saying to the good? So to start off with, it's a two-dimensional. And he's saying that, look, we found two good unperturbed states, all right? So in other words, and they're a linear combination of psi A0 and psi B0. So this was a 2x2 matrix that when you perturbed it, it was non-diagonal. So they diagonalized it and they found the good eigenfunctions. And they're saying these are the good eigenfunctions. All right, and they're saying now if you take those good eigenfunctions and you try to make the W matrix again, you know, what happens, that first line is that psi plus 0, psi minus 0 equals 0. What terms are those in terms of the matrix? Dahlia, I think you just said it. Those are the off-diagonal terms in the new good basis set. And they should be 0. Right? And then the next thing that they ask you for is the psi plus h prime, psi plus 0. And those are going to be our,
Easier.
those are going to be our,
Off-diagonal energies.
they're going to be our diagonal energies. So this is all being done in the good basis set now. This is all being done in the good diagonal basis set. So what they've done is they've tossed away the answer psi A0 and psi B0, and they're using a new basis set, which is a linear combination of A0 and B0. And so this is the good basis set where everything's diagonal. If everything's diagonal, that means that the overlap matrix with the perturbed and Hamiltonian should have, the diagonal term should be the eigenvalues, and the off-diagonal terms is 0, which means that these bases are no longer mixing with each other. And if the bases are no longer mixing with each other, what you're saying is, I found the good eigenfunctions, the eigenbasis. Okay, so that's why I know that a lot of this problem was done out, but I felt like this was a good problem to talk about all these things. Okay? It's very powerful stuff. Let me just go one step further and show you how I did it in Maxima. All right? So in Maxima, for this problem, this example problem, I simply did this. I input a matrix. So input a matrix. And then it asked it, and I made it a 3x3, and I gave it a name, and I called it A. All right, and then when I was able to input it, I put in a 1, 0, 0. A 0, and then kappa, no, 0, a 1, kappa, then a 0, then kappa, and then 1. And then what it does is it goes out 1%, all right? So this is the first element.
No, what's the
It's
percent?
output 1%.
Percent zero.
Yeah.
Percent zero.
So then the next line I ask it, I just say eigenvalues. And then what it does is it automatically does percent, and percent takes the last input. But if you wanted, you could get rid of the percent and just put A. And what it will do, it'll get the eigenvalues of A. And when it did that, what it did is it gave me something that looked like this. It gave me something like a 1 minus K, a 1 plus K, and a 1.